I want to talk about the challenges we ran into when modeling high shares of very renewables and sector integration in the Osmosis project, and how we developed a tool named AnyMOD to address these challenges. Modeling an integrated energy system implies to model a lot of sectors, and is usually done using a reduced time series to keep models computationally traceable. However, we discovered that in systems characterized by high shares of very renewables, reduced time series can actually lead to very flawed solutions. For instance, capacity investment computed with a reduced time series can lead to substantial shares of lost load when evaluated with a full time series. This research will be presented in greater detail at a workshop that I've linked in the description. To address this, we developed an alternative graph-based approach to decrease model size. The key idea of this approach is to vary the level of detail by energy carrier within the same model. For example, this approach can be used to apply an hourly resolution to the power sector to model solar and wind, but at the same time, the gas sector could be modeled at a daily resolution. This does not only decrease model size, but also reflect the physical properties of gas and the gas transmission grid much more accurately. To implement this approach, we developed a framework named AnyMOD. You can find the GitHub link in the description as well. It is implemented in Julia and can be used to automatically generate capacity expansion models applying this graph-based approach. Another advantage of the approach is that a flexible substitution of energy carriers can be modeled. For example, it can account for the fact that fossil and synthetic gases are created differently, but can be transported, stored, and used by the same technology. This graph shows that compared to a conventional approach, the graph-based approach is capable to decrease model size and computation time, but does not greatly alter final model results. So far, models created with AnyMOD are limited to a single weather year. However, we aspire to cover several weather years within the same model to achieve an even better representation of weather-driven fluctuations. For this purpose, we are currently implementing a single-stage stochastic approach where each year of capacity investment on the top level in this graph is analyzed for different historic weather years. Since this will greatly increase model size, standard solution algorithms will require way too much time and RAM to solve such a model. Therefore, we started working on a distributed solution algorithm based on Benders decomposition. In this graph, you can see the convergence of that algorithm. So far, we did achieve a substantial speed up compared to the standard Benders implementation, but at least on our small test problem, we are still outperformed by Grobi.